Good morning, everyone, and welcome to Hot Sauce 2026. I am delighted to introduce our first keynote speaker, Deian Stefan. Deian is an associate professor of computer science and engineering at UC San Diego. He does research on security and programming languages, and he has done some really cool work building secure systems that are deployed in production, and you will hear about some of that today. In addition to his academic research, he's the co-founder of Cubist, which is a security and infrastructure digital systems platform. And he was previously a co-founder of Intrinsic, a runtime security startup that was acquired by VMware in 2019. So we're delighted to have Dan, and when you're ready, go ahead and present.
Awesome. Thank you for the introduction. And I'm gonna try this with the browser and see where things go. But okay, so I'm excited to talk about kind of a bunch of the work that we've done on using kind of formal methods, and here I mean more like lightweight formal methods to um, harden bits of different browsers. But in particular, the one I want to talk about is our work trying to use language-based techniques, verification, kind of language design, and things like that to make Firefox more secure. Um, in general, kind of what we work on, or at least my group and my collaborators, we kind of focus on solving security problems, in particular system security problems, and using programming languages as the way to address these problems. And a huge reason for this is because um, we think that if you focus on the language, the tools that programmers are using, we can actually get rid of like whole classes of bugs instead of like you fix one bug and then the attacker like finds a new bug and then you're in a kind of arms race against what the attackers have. And I think like we've all seen in the last month pretty interesting results that are basically showing that hey, we can find bugs pretty well if we have a pretty powerful model. As one other flavor bits that I can point you to, there's a talk from Vivian from our group. He's going to talk about how we verified bits of the talk operating system and kind of like in the process, we found some bugs there. Okay, so I'm going to talk about browsers, and the reason that I would talk about browsers, and sorry if some of you have seen this talk, is because I see browsers as basically like the modern operating system, and it's kind of awesome, right? Like if we look at it, you can run any app instantly, you can publish and update apps instantly. Like we don't have to, as users, think about the malware. This is kind of awesome. Just go to your browser, type in a URL, and then you're good to go. Um, it's kind of also scary, right? So like, okay, if we look at the reality of the things you can run any app, well, it's maybe not great. Publishing app updates is great if you're like a PM somewhere and you're like, I want to now like charge users for new like instant app features, and I can totally like spy on my users when before I had to like give them an actual physical copy of a piece of software. And we don't have to worry about malware. Well, kind of we do because like so much of the web is basically malware. But okay, that's not the scary part that I want to talk about. That's for somebody else. The part that I want to talk about is kind of if we look at all of this, the ability to just like run code and get updates and ship new things to users, like as awesome as it is, it really is kind of like just from the user perspective, running untrusted code all the time. And a lot of times this is coming from the pits of the internet. So it's not just that I'm running this like in this particular case, the PowerPoint from the Microsoft like website is like if I'm visiting like a big enough web app, I am pulling code from random parts of the internet, and we've seen again kind of like supply chain attacks and things like that where people are shipping malware directly to users. And the reason this is really scary is because, like, underneath the hood, these pieces of code are just C and C++. So they're like unsafe, gigantic systems, and like any other unsafe, gigantic systems, we see basically exploits in the wild where people are using these uh, 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 vulnerabilities of different parts of the browser, like even things as simple as like rendering an image to exploit and target users. And the trend is not looking great, right? So like just taking kind of a screenshot from one of the blog posts written by Anthropic and Mozilla, um, Opus 4.6 found dramatically more bugs than we've seen over the last, couple of months, spanning into like the last year, before, right? So it's clearly that like the number of bugs are going up. It's not clear if we're gonna like, similar to fuzzers, um, have just an asymptotic drop at some point. Like it seems like that's potentially the case from like stuff we've looked at in other kinds of systems. But nevertheless, like there are lots of bugs, and it's really hard to keep up with actually fixing these bugs. So we should be expecting like more things like this as better, newer models come out. So what can we actually do about this if we're step back and think about the problem? Well, one thing we can do is we can rewrite the whole thing in Rust. And if you're in the business of like LLMs, I think like it's pretty reasonable to think about this thing as a, okay, like this is a practical way to eliminate whole class of bugs. Rust is a great language that's designed for safety and security in mind. So we would be like actually like meaningfully like improving the security of a browser like Firefox. And again, like if you're end up kind of thinking about what do you rewrite? Well, if you have one hammer, you'd say like, let's rewrite the whole thing. And we see like that there's actually efforts to rewrite gigantic piles of C and C++ code bases wholesale. For me, it's really hard to think about taking a giant browser and rewriting the whole thing. I think we're quite far away from that, and I'm not sure that necessarily throwing this hammer at it is the right way to be thinking about how we structure systems like this, because I think we're gonna see different classes of bugs that exist in Rust systems. So like one of the things that we looked at in the WebAssembly world is the wasm time runtime. This thing is written in Rust. There's unsafe bits in Rust code, just like anything else, because we need to think about how do we compartmentalize. That inherently means kind of doing certain things unsafely. And then like we found bugs there as well, right? So like you'll find different and same classes of bugs even if you rewrite the whole thing. And I think like it requires more thought into the software architecture part of it than simply just trying to like rewrite each component. So like what should we actually rewrite? So I think like what I look back to, and this is now kind of an old post from the P0 folks, but it's basically looking at like what are people actually exploiting. And I think we're seeing this also with like the new bugs that are being reported in Chrome and Firefox and Safari, where like we really should be focusing on the JavaScript engine and third-party components, things that are handling the actual interactions with the DOM. Okay, so we look at these two bits, rewriting them in Rust doesn't completely make sense for a few reasons. I'm not saying we shouldn't do this. I think like if we can, like I think that'd be pretty interesting and pretty reasonable. But like the reason it seems to be a hard problem is because these are millions of lines of highly tuned C codes. If you take a decoder, this is like code that's been like slapped over and over for like the last 10, 15 years, and it's really really fast at doing this particular thing, which is like decoding images or rendering glyphs on your page. So like rewriting is a huge effort. Testing it is a huge pain, and kind of we've seen efforts to do this, and most of them have failed. Some have succeeded, but I would say like on average, these things have failed because like we just have like regressions that we just don't see in these old codecs. Um, Things might be changing by using things like LLM. But I think the hard part to think about is not just we're going to rewrite this component. Great, now it's in Rust. We need to think about the boundary because you're not going to rewrite the whole thing. And now like the interface between this Rust piece of code and the C++ piece of code, dude, there's going to be bugs at those boundaries. We've seen these bugs already creep up in real systems, and we don't, I would say, have amazing techniques for yet handling all those boundary conditions because the languages are just different enough where there's enough of an impedance mismatch between the two that we still have to solve in practical ways. But I think that's a fun challenge. So like I think like if you're working on this, like I'd love to hear more about it, and I encourage folks to at the very least like not write new systems in C and C++. Um, um, the other reason, I guess, like if we were focusing on efforts on what to rewrite, the reason I don't think these are necessarily the most fruitful things is like we don't actually always need fine-grained memory safety that we get from Rust. Like it turns out that actually just shoving the thing in a box, getting that box right is actually enough. And like we're better off building these boxes that help us actually just shove old code in there and let that code be and just do what it's intended to do, which is kind of render glyphs for us. And then similarly for the JavaScript engine, like we could rewrite it in Rust. I think that's something actually like we're looking at building a new JS engine in Rust because like I think it's like an interesting research exercise to figure out, okay, like what do we actually get from this? But in general, like if you rewrite it, like the huge wins aren't immediately obvious, right? Like the bugs that we're seeing in JS engines are largely in the generated code. They're not in the JS engine itself. So like meaning like the compiler itself is not the thing that we should be worried about. It's really what the compiler actually produces. And here it's about logical bugs, less so about memory safety bugs in the compiler itself. Okay, so in the rest of the talk, I'm going to talk to you about how we tackled bits of both of these issues and how we focused on eliminating security bugs or like not treating bugs in third-party components as security bugs. And we looked at rewriting parts of the JS engine of Firefox to verify that the thing is actually safe, no matter what code it generates. Okay, so I'm going to start with RLBox. This is our fine-grained sandboxing framework. And kind of looking back of like what we were trying to do with this is we're taking Firefox, breaking it apart into different components. Specifically, we're going to take libraries like libjpeg, libogg, which render images and fonts and so forth. And we're going to shove them in their own fine-grained sandboxes. So this is all running within the same process, but now each bit is running in its own isolated region of memory. So like what this eliminates is the effort to actually rewrite these highly tuned libraries. And instead we can take off the shelf libraries. In our case, we're going to compile them to WebAssembly and link them back into Firefox. And the regression should basically not be existent. Like if we find any regressions, that's a bug in the sandbox itself. We fix it there and then we fix it for every library. Um, and like, well, again, this kind of like works pretty well because like for most of these libraries, all we really care about is this core grain notion of safety. We don't really care about fine-grained memory safety. Now you could say, okay, like I'm rendering an image. If I'm rendering the wrong thing to the user, now I'm attacking users in this particular way. If we start caring and seeing those kinds of attacks, I think it's totally worth rewriting this thing in a language where we can actually say this is a correct implementation of libjpeg. I still think we're like far off from those kinds of attacks. We're still into kind of more primitive pitchfork and fire types of attacks that we're seeing for real. Okay, so and kind of like the other bit that I think we have beyond Rust as a hammer is that WebAssembly is actually a modern bytecode that was designed with semantics in mind. So we actually have a language where we can reason about what is this actually giving us, both at the language level and when we compile this thing to arbitrary code. And like we can actually think about isolation in principled ways instead of kind of the more bits and bytes type of like masking approach to SFI where it turned out to be pretty hard to implement in practice without introducing a bunch of bugs for real. Okay, so in the real world, there's also like means that we can use off-the-shelf, compilers like CraneLift. What we end up using is wasm2c, but like the idea is there's many compilers of WebAssembly. It's a nice enough and simple enough bytecode that people can do this. And in the ideal world, things just actually works, right? So we have like the thing that we want on the left, which is Firefox and a bunch of sandboxes, and we should be able to just take an off-the-shelf compiler, take libjpeg, compile it with our like wasm compiler, which gives us memory isolation by essentially just instrumenting every read and write to ensure it's within your region of memory. And it does essentially control for integrity to ensure that, hey, you're always jumping to these basic blocks that have our read and write being guarded. So like that, we can just take it off the shelf compiler. Now we get isolation for free. And then step two is we modify Firefox to use this sandbox library, right? So like if you were to like rewrite things in Rust instead of use WebAssembly, step one will be different, but step two should still look somewhat similar in that we need to rewrite this piece of code to now deal with this newly isolated and newly untrusted component. Okay, so in practice, what we found is that like actually step two is the thing that's a huge nightmare, right? So what you have to do is you have to decouple the library from the rest of the application. So like this means we need to decouple whatever shared data we had between Firefox and the library. We also need to now think about where is the control flow across this boundary. So when I pull in a library, I don't think about these things. I just call a function, I pass it data, it gives me data, and like all this thing is basically implicit. So like the kind of like object graph is not something that we're explicit about. It's not something we think about. So if we're about to decouple the library from Firefox, now you go back and draw the boundary conditions between these two different components. um, the other bit is when we are going to sandbox a library, and if we're going to use something like WebAssembly, this has a different machine model from potentially your application. So if you're on Firefox on a Mac device, let's say it's 64-bit. We have 64-bit in Firefox land. In WASM land, we're still a 32-bit machine. So when we convert pointers, when we have pointers going across the boundary, we have to deal with that. When we have structs, we need to think about how structs are packed across the boundary. And importantly, like we can't just treat this as an IPC layer where we serialize the thing and then serialize it on the other side. We have to lazily actually copy things across the boundary, both because like it's actually really hard to serialize the whole object graph. You don't always have all the bits that you want to serialize, but it also would be really expensive. So for like at every function boundary now copying a ton of data and serializing and deserializing, this now adds to enough overhead where like you wouldn't practically ship this thing. It's just like way too expensive to do that. And we kind of like already are seeing this with the amount of process isolations the browsers are doing, right? There's certain things that they're doing and shoving in separate processes and doing this kind of serialization. And basically, like both Chrome and Firefox have hit the limit of like we can't split things into more uh, processes, both because it's too expensive to create a process, but also because the boundary crossings are way too expensive for libraries like let's say libjpeg. But okay, so like in our world, what we're going to do is we're going to decouple the library. We're going to figure out how to share data across the boundary. And now that we're saying like, okay, libjpeg is no longer a library that you just use. We're saying libjpeg is an untrusted piece of code. So like what we're worried about is a bug in libjpeg getting exploited and that turning into an exploit in Firefox. So what this means is we need to actually go look at where we call libjpeg functions, where libjpeg calls us, and start sanitizing and validating the outputs coming out of this now untrusted library. Previously, you just call a function, you get some value, you might use it to access memory. Now we can't actually do that. Now we're saying like if the attacker like hijacked the control flow of this library, they might give me a malicious value, hijack the rest of my browser in turn. So we need to actually go back and check all the bits that before we were like, this is totally cool because it's effectively a piece of code that I trust. Okay, so what this looks like, if we take a simple application, like in this case, like I just have like the equivalent of hello world of using libjpeg or like a simplified version of libjpeg. So I'm going to have basically a struct called jpeg decompress struct. Then I'm going to have something that handles error messages because like we're going to need to think about like what happens if I have a decoding error. Then we're going to call jpeg decompress. We're going to like access fields of this struct that's shared across the boundary. We're going to get bytes from the network in Firefox land. We're going to read those like the headers from those bytes, and then we're going to actually look at the rest of the bytes, which we're now going to treat as the image that we're going to decode because, well, we had a header that told us how big the image is and what kind of image this is, right? And then we're going to render that thing, which means we're going to copy that thing to some other buffer where we're going to render it on screen. Now, you don't need to understand this piece of code. That's not really like the point of this slide. I just want to kind of give you a flavor of like, okay, that there are a bunch of things happening across the boundary. And if we're going to now sandbox this library, we need to make these things explicit. So like when we allocate a struct in libjpeg now, this actually is a struct that lives in the sandbox. So we're going to need to like malloc this thing in the sandbox. When we call a function like jpeg create decompress, this is a JPEG function, so we need to adjust the pointers or the values that are going into this function as arguments. So we're going to need to marshal those things. We're also going to need to adjust the calling convention because Firefox is one ABI, WASM is the other ABI. So we need to actually deal with all these things. If we had structs like JPEG image, and you want to access a field of that struct, now you actually have to adjust for the fact that structs in Firefox versus structs in libjpeg, they're slightly different. So we need to actually adjust for like the field offsets there, for the representations there. And then like if you like just keep looking at this thing, it gets really gross really quickly. And the thing that really like is happening here, if we look at like, okay, like why is it so gross, is basically like all the mechanisms of your sandbox are bleeding back into your application. So like basically this is telling us like, hey, this way of doing sandboxing is just like not a reasonable abstraction for building systems. And like we've done this, and like version 0 of RLBox was exactly this. And we looked at this piece of code and we're like, we should throw this thing away because it's just like actually less safe than where we started from. We're not confident that we got a bunch of this code right, because any bug here is basically now a bug in Firefox, and I can just exploit that thing from the JPEG land. Okay, so um like to give you like a sense of like how bad of a problem this would be, even if we were saying like, okay, it's worth doing this because we're seeing so many exploits in the wild and all these third-party components. That was for a simple function. You can imagine like if you're actually looking at the like decoding in Firefox itself, it spans many functions, many classes. This is C++ code. It's way harder to actually keep track of where the different control flow boundaries alone are. Right, so like we're exposing all the sandbox details. The code itself becomes really unmaintainable, right? Like if we're looking at who's responsible for this piece of code, it's not the security team. It's going to be the team focusing on rendering glyphs on a page, right? And those folks don't generally want to think about sandboxing. Like they are um I think a lot of folks hacking on browsers are actually security conscious, and they're like fully aware and thinking about like the user and like, okay, this is like untrusted content that we're working with. But still, like this is not a security team that's all they're dedicated to is getting these security checks right, right? So they're focusing on making sure that we're rendering this thing fast enough. Otherwise, like our competitors are gonna like win in different ways. Um, and finally, if you were thinking about starting from Firefox and porting it the way we just saw, testing this is super nightmarish because, well, you need to port the whole thing first, then test, and like we're not very good at writing that kind of software and testing things this way. And separately, you can't ship this thing piecemeal. So if we want to ship this on Linux devices and then on Mac devices and then on 32-bit Windows devices, we might not have the same sandbox capability. Like it's not necessarily that you can use the same WASM sandbox across the board. So that becomes a nested, basically, or like gross code that basically has a bunch of like macros and pound defines that are basically saying like, if we're on this platform, do this. If we're on this other platform, do this other thing. So like that fails super, super quickly and super miserably. And even if we were to do this for one thing, great, some wins, but like the number of libraries that we have to think about is way bigger. So like you would just give up, right? And this is like what we saw from other folks kind of trying to do the same thing. So like Ben Laurie had this tweet a while back on, hey, we're like looking at experimenting and sandboxing libraries, and the approach was similar to kind of like what I showed you here, and really like it was way too much to handle because there's so much sharing and so much like both data and control flow across the boundary that is just like really hard to keep track of. So they kind of gave up at that time trying to sandbox libraries in this particular way. But if we look at the problem with a slightly different approach than kind of the um, the sandboxing folks have been looking at over the years, in particular, if we look at it with our programming languages hats on, um, this can actually be a problem that we can solve using types. So actually, Jonathan and folks like that have done a bunch of work on kind of gradual typing and using that to solve similar type problems. And it seems like this is actually kind of a problem where we can, like, given types, actually make this whole problem way better. And what I mean here is we're going to use types to make the data and control flow explicit instead of this implicit thing that we then have to then rewrite one line at a time, and hope that we got it right. And if we use types to make the boundary conditions explicit, we can also use type to hide and abstract away all the sandboxing details. So we can automate all the conversions between the different machine models. We can do the data marshaling automatically because like our types can encapsulate like this kind of information. And types also would make tracking untrusted data across the boundary really explicit, right? So like we would know that we're missing a security check because we now get a type error that says like, hey, you need to go and validate this thing because this thing has a different type from what it did before you actually retrofitted sandboxing around this thing. And if we look at these types as gradual types, it allows us to retrofit a browser piecemeal. So we can rewrite one line at a time, force the typecasting for the rest of the thing, test it, and then rewrite the next line, and so on and so forth. And as you can imagine, like nowadays, this is actually really, really amenable to taking something like Claude and just saying like, go sandbox this library using RLBox. The way I like to look at this thing is if we have the figure here on the right is like really like the boundary between libjpeg and Firefox is this like jagged thing, and RLBox is the thing that helps you glue it together to the rest of the browser and actually get those conditions right. Okay. And kind of looking back at like what is this actually giving us? I think types is the key to making sandboxing composable abstraction or a useful abstraction. Otherwise, we have this thing that forces you to reason about internal implementation details in your application. So like the sandbox is less of a useful abstraction if I have to always deal with the sandbox boundary when I'm trying to use this particular abstraction. So it's as if every function that we expose now has to think about the implementation of the thing. We're pretty bad at building systems in this particular way. Um, okay, so what does this mean if we look at the example that we started with? Well, again, everything is now explicit. So if we have JPEG read header like we did before, now we're going to get a compilation error saying like, hey, JPEG lives in a sandbox, so you have to actually make the cross-boundary call explicit. So this means we're going to do sandbox.invoke, tell it which function we want to invoke with, and then the arguments to that function. And then we're also going to check to ensure within this kind of implementation of invoke that we're calling JPEG read header with the right types. When we have data that's spanning the boundary, this data will be marked tainted. So like when we get, say, the image size, which is a field of a struct called JPEG image, which lives in the sandbox, well, this thing lives in a sandbox, so we should treat it as untrusted, which means that the arrow type is going to give us a tainted uint32t instead of a uint32t. So this means if the thing on the left is no longer well typed, we're going to get a type error saying like, hey, you should treat this thing as tainted. And importantly, what this means is when we get to step 3, when you're about to use tainted values, you can't use them to do to kind of treat them as um, the underlying type. So you can't take a tainted uint32t and say we're going to treat this as a number. You have to actually validate that number before you use it in something like memcopy. So in our particular case, we would have to take size and then copy it into Firefox memory from the sandbox. And then we're going to verify, for example, that this size actually is less than whatever the memcopy we're about to perform. So this was like one way to ensure that we're not memcopying beyond the boundary of the buffer that we're copying to. Right. So like as a user, like you might still get this verification wrong. And over time we've gotten some of these wrong. Um, but it is like a particular like a single point where we can point to and say, okay, this is where you need to really scrutinize this piece of code and get this right. Everything else we don't have to really think about. It's just now this boundary condition where we have to validate data. Okay. Um, so again, like if we like look back to like what is the goal that we wanted from something like Rust, it's to eliminate whole classes of bugs. Well, it turns out we can get the same thing by taking WebAssembly and a type-based framework like RLBox, and these together give us a way to like eliminate all these classes of bugs and not have them be security bugs in our giant system. Now, in practice, like shipping this thing took a lot longer than kind of we initially thought. So we thought this would be like a quick summer project. Then we hit the like, okay, this is actually like really like a hard problem to just use sandboxing in general. Um, but then it was so this was like in early March. We started with actually like shoving things into Firefox proper, shipping it, and um, on Linux where we had a compiler for WebAssembly, but getting it across all of Mozilla's platforms, including 32-bit Windows and parsing more libraries, took a fair bit more work. And kind of this work we can kind of think of as both performance work and security work. So like first as like actually having cross-platform support, we need to like support all these different operating systems and all these different architectures where we might not have an off-the-shelf sandbox we can just use. And if the performance of our sandbox or if the checks at the boundary are super expensive, or if the sandboxes use a ton of memory, or if like our code size is so big that on 32-bit Android, it's like too expensive to use this thing. These are all things that we actually have to think about because in the real world they matter, right? Like if my sandbox is like using up all my memory, I'm probably not going to use a sandbox or my browser will crash and we have to deal with these kinds of things. And finally, there's things like build time. So if like now the build time of Firefox is twice as long as it was before because we have to do like the sandboxing thing, suddenly like a bunch of other people are upset at this, and understandably, everything is more expensive because of this. Um, okay, so I'm going to talk about like how we solve some of these problems, um, and kind of like unveiling some of the bits or like our assumptions over time, and in particular like how some of our assumptions were wrong. So first, we were looking at WASM as kind of the thing that gives us isolation for free. And what this means is if we look at a bunch of kind of compilers, that they basically are like, hey, you can run a bunch of code at near native speeds if you just compile it to WebAssembly and it's isolated from the rest of your environment. Um, in practice, it really depends on which compiler and like what you mean by like near native speed. Like, does that mean like 1x or does it mean 2x? Like, how much is that isolation actually worth it? And like, maybe 2x is fine, but like, maybe not in every case because like in certain libraries, like we really do care about the sandbox performance. For others, maybe a little bit less so. When we started this whole thing, we actually started with a somewhat crazy idea of taking WebAssembly, compiling it to C, and leaking that piece of code back into Firefox. But we decided like, hey, this is like a ridiculous thing to do. We shouldn't be like using C even as an intermediate language like this. So like we after December 2018, we switched to Lucet, which was one of the first compilers written in Rust to actually take a more principled approach to compiling WASM. Um, and using kind of Lucet at the time. This was like Cranelift plus the Lucet runtime. That's how we actually shipped the first version into Firefox. But Lucet was deprecated, and like a little bit later, like maybe 2 years later, and that's what like kind of ultimately became Wasm time. Um, but when we were trying to actually ship this thing, Lucet was still, I would say, in the early stages. So like a lot of things were experimental. Like folks were trying to implement new techniques in this compiler. And what this basically meant is we were lagging behind on where Firefox is if you take a like decades old compiler like Clang. So like we didn't have all the platforms we wanted to support, and the performance wasn't anywhere near um, where a mature compiler like Clang is. Now things have changed since then. I would say like Wasm Time is awesome. So using Wasm Time nowadays like really makes sense. But where we ended up kind of a few years after December 2018, so this was like in 2023, is we went back to Wasm to C. Um, so this is still something that I'm kind of like looking back at and trying to see like, okay, do we want to redo this part of um, our framework because it's kind of gross. But there's also certain bits that are like I would say pretty interesting on compiling back to C. So first, adding new enforcement mechanisms to WASM C is really easy. So we can kind of change different ways of instrumenting our reads and writes. And this is really important if we're like, okay, on like Windows 32, we're gonna use masking instead of bounce checking, which means we're also like just violating WASM semantics, but it's the best we can do if we want to have a tight sandbox. Uh, but on like a different platform, we can very like easily support WASM kind of like off the shelf using page tables to ensure that we're actually like drawing a good sandbox boundary. Because we're compiling to C, this means we have platform support across the board. We just need a tiny amount of runtime to be able to like call into Firefox. This is really like not big code, so like we can like write that piece of code, but like we get things like compiling to ARM, to x86, to any other platform basically for free. And we're getting this for free because we're going through Clang and GCC, right? So like it's not just free, we're also getting like free optimizations that these folks have implemented over the years. And the performance is obviously going to be much better than if we were writing a new compiler from scratch nowadays. It's a different setting from if you were like looking at WebAssembly as running untrusted code. In our particular case, we're taking a library that we nominally trust, but is exposed to untrusted input. So like if we were worried about bugs in uh, the library, oh sorry, in exploits in the library itself, it would be a completely different thing. And I would not say like this is a reasonable path to use. We should use something like wasm time. But because we're saying like all we care about is untrusted input instead of untrusted code, we're able to cheat in this particular way and not necessarily worry about the kind of classic bugs that we would be worried about in a compiler like Clang and GCC. Okay, so that's kind of I would say like the obvious performance thing to like solve is like the sandbox overhead itself. The less obvious performance problem after we got the sandbox to a reasonable state was that like crossing the boundary was really expensive. So like there's libraries that are you need to like cross the boundary every time you're rendering like one like glyph on a page. So when we're rendering here the letter O, right, we're going to cross the boundary. When we render the letter B, we're going to cross the boundary again. So if you like do many context switches across the boundary, this could be like a ton of overhead, and this overhead can be on the order of like 200 to 800%, which means like now like rendering a page takes dramatically longer and it's user noticeable, which means we're not going to ship a sandbox thing because nobody wants to wait for a page to load this long. Now the fix to actually eliminating this overhead was kind of an insight from, I would say, formal methods here. So like if we look at what is our sandbox implementation, well, it's WebAssembly, and it turns out WebAssembly has these really clean semantics. And just by compiling to WebAssembly, we end up having like a structure at the binary level, and this structure is actually turns out to be enough structure to say that we can remove the context switching code, namely the code that would save and restore registers across the boundary, and just get rid of it completely. If you were using a different sandboxing mechanism that's not WebAssembly, like let's say if we were doing classic native client style sandboxing, then it's actually not safe to remove the context switching code. We need to actually save and restore registers and clear registers and do all these things. But it turns out because we're using this different sandboxing technique that has some structure at the binary level, we're able to just say like get rid of all the register saving code and clearing code at this particular boundary. So this basically means we now actually really have a function call across the boundary and not this beefy context switch that looks like an OS context switch across the boundary. Okay, there's lots of other things that kind of went into getting the thing over the fence and making the performance and security work out. I'll say like pretty much the underlying lesson is wearing our language-based techniques hat is what saved us every time. Otherwise, there were like definitely points where we were like not thinking about this in a principled way, and it's like the whack-a-mole game kind of was clearly becoming like would have become an issue if we weren't thinking about this. Okay, how do we frame this as a types problem? How do we frame this as a verification problem? Okay. So what I'm going to like maybe just show you is kind of like what the performance overhead what is like today after having done a bunch of these optimizations. And what we're seeing is on 64-bit the performance of rendering of parsing SVGs, for example, is on the order of 7%. On 32-bit, it's 20%. And what this means in practice is that this is actually reasonable enough for us to ship in Firefox. And the reason I want to bring up these numbers of 7 and 20%, or even like on the bottom here, we have for WOF2 decompression, it's like the mean is 10% overhead, is because kind of the kind of rule of thumb for a lot of folks has been if you're security mechanism imposes more than 5% overhead, we are just not going to ship the thing. Well, in practice, like it actually might be fine. Like in fact, like when we shipped the first version of a library, the in sandbox overhead was 100%. But it turns out like this is not user perceptible, right? So I think like even thinking about performance as a like, well, what does that actually mean for the user? I think it's an important thing to like rethink instead of saying we're only going to use the sandboxing mechanism if the performance overhead is under 5%. Like it turns out that actually like stepping back and looking at the macro benchmarks instead of the micro benchmarks really does actually matter. Um, Okay, so like, what does this mean? Like, if we look back, okay, we sandbox all these things, the performance is pretty reasonable. Looking back at um, kind of libraries that have sandbox, we sandbox in Firefox, things like libexpat. There have been a bunch of bugs in libexpat that folks started looking at. Part of it was after we and Mozilla, well, I guess I shouldn't take any credit. Mozilla added RLBox to their bounty program, and folks were like, okay, we're going to try to break out of the sandbox. And the way they did that is by finding bugs in libraries like libexpat. So there's a bunch of CVEs that folks found over time. There's a classic memory safety bugs. There's probably like 2 times as many now if you threw something like Claude or Codex at it. I'm sure like there are lots of bugs in this piece of code. Not necessarily because it's bad code, it's just C code and it's complicated because XML is really complicated. Um, what this meant for Firefox in particular, and Firefox is not the only browser using libexpat, is that these CVEs in libexpat were not CVEs in RLBox, and they were not CVEs in Firefox. So like the 4 a.m. kind of wake up, there are a bunch of O days that people have revealed are no longer things that you have to necessarily worry about. You can treat them as bugs that you'll fix in your normal release cycle. So like the amount of engineering effort that you need to spend on is less than it was before because, well, they're not actually security bugs. They're just bugs. And like any other bug, well, we're going to fix it. But in general, we don't expect people to like really care about their XML render not rendering XML if they're shoving bad XML at it. It's kind of like, well, user, please don't crash your own XML parser. Um, as long as that can't turn into I've exploited the rest of the browser, I think we can even deal with some of these crashes. Looking at so like what this basically again what kind of means is third-party libraries bugs there are no longer bugs in or not security bugs in Firefox. This doesn't mean that like there are no security bugs that we need to think about. Like again, like you have to get the validators at the boundary between libexpat and Firefox right. Over time, we've gotten some of these wrong. I think it's interesting to like look back at them and trying to figure out like, okay, how do we actually ensure that we got our validators right? And I think there's like again interesting verification techniques to use here. But these or the number of bugs that we've seen in the validators is dramatically less than we've seen in libexpat, and part of this is just like the sheer amount of code that expat has versus the amount of validators that we had to write. So like you have to write on the order of like maybe a couple of dozen validators versus we have hundreds of thousands of lines of C code. So like just the numbers are in our favor here. And I guess like one other bit I'll mention is like what we saw historically was that actually even porting RLBox back to previous versions of Firefox made more sense than trying to patch one of these libraries and integrate them back into Firefox. So sometimes kind of like your sandboxing technique, your isolation technique might be an easier thing to backport than the code itself. Okay. The other thing I guess I want to look at is instead of looking back is like looking forward. So like one of the things that we're starting to play around with is just sandboxing more libraries. For all the libraries that kind of we sandbox to date in Firefox, we manually like implemented these libraries ourselves. So like we manually retrofitted, not implemented the libraries. But this is again a mechanical process, right? So like I mentioned, that this is a gradual types problem, and it's very much driven by like this is a type error, go fix the type error. This is a type error, go fix the type error. So like that's how like the sandboxing process is nowadays, which is basically like a perfect fit for something like Claude, where we just say like we want to sandbox this library. It now has a loop of like I got a type error. Let me turn that thing into a tainted thing. Let me compile it now. Do the same thing. So like there's really like now I think effectively almost free engineering resources that we can throw at this problem by just using an LLM. And yeah, I guess we'll still need to get the boundary conditions right, which is where I think like we'll want to still like focus ourselves. But I think again, program analysis and verification techniques are a really good fit there. I locked myself out of my machine. Okay, there we go. We're back. Um, okay, so I've been talking about the third-party components. What I want to spend the last kind of 14 minutes on is Icarus and what we did on the JS engine side of things. So here is where we use verification to actually verify that our JIT compiler is producing code that is secure. So again, like this is to me an interesting problem because it's a verification problem by definition, right? Bugs in the JavaScript JIT engine, these are logic bugs. If we port the JS engine to Rust, we're not going to fix bugs in the code that that thing produces. We'll still need to actually produce code that is safe. Now, Rust might help us here, and I think that's one experiment that we're starting to play around with. Uh, but at the very least, like we don't know to what degree it will help us produce more correct code, and we still have to deal with these logical bugs. And I guess the bit that I want to like maybe scope this problem down to is what we looked at. So if you look at a JS engine, these things are gigantic. They're like evolving all the time. Like since we like even did this work, like this thing has changed pretty dramatically. But like what this tells us, at least from a what techniques we need to use to actually verify bits of the JS engine, especially if we want to like go broader than what we did, is we really need an automated and like approach to actually getting the verification the verification results, and we need an incremental way to actually port things, right? Like if we're saying like stop today, we're going to take SpiderMonkey as it is, we're going to rewrite it in a theorem prover, then we're going to give you C++ code that you can integrate. By the time we finish that project, this thing evolved dramatically. So we need to somehow keep up with what folks are doing in the JS engine and verify that code and give them tools so that they can keep improving um, the JS engine while the kind of verification tools serve as guardrails for their work. And this is like what we designed Icarus for. So you can think of Icarus as a domain-specific language and like verification framework where you write your JIT compiler in our DSL. So this is domain-specific language. You write your compiler much like you would today in C++, but with kind of first-class primitives for language design. And what you get at the end is a thumbs up, thumbs down on this is safe or unsafe if you've inserted the right kind of assertions and verification conditions. And you're going to get out a JIT compiler implemented in C++ that you could integrate back into the browser. I'm just talking about browsers. You can obviously use this thing for any other kind of things. It's just browsers is what we've been looking at. And in particular, the thing that we looked at porting to Icarus was the cache IR part of Firefox. And this is the part that is implementing the inline caches of the engine. And now to give you a sense of why we built a whole new DSL and whole new framework for this, I want to look at a particular bug, in particular mishandling property access for typed arrays. So this was a crash from, I guess, now more than 4 years ago. In that was found by a fuzzer, I think after like a fair amount of work. Okay, so what is property accesses and like what does this look like underneath the hood before we look at like what that bug actually is? Well, in JavaScript we have something like foo.bar, and in a reasonable language, this thing would just compile to like a register relative read, right? Like we're just reading bar off of foo. This should just be like an offset off of this particular object. And in JSLand, this is like totally not the case, right? So like it might depend on it, like what foo is, what bar is. These might be dynamic properties. Like bar might actually be a getter function. Foo might be a proxy object. Some bits might be natively built in JS objects. So there's kind of like 32 different paths that you can take to just figure out something as simple as foo that bar. All right, this is a really gross language. So this is like where the JIT engine comes in and says, okay, we're gonna like try to make this fast because otherwise we're evaluating those things like every time. So inline caches are kind of the first line towards producing optimized code. And the way you can think of this is when we're first executing this JavaScript code, we're going to take the generic path. So we're going to evaluate those 32 different conditions. The second path, so the second iteration and onwards, we're going to have a specialized path that says, okay, like we know something about food, we know something about bar, so we're going to take this faster path instead of the kind of evaluating, is it this, is it this, is it this, is it this, or is it that? Um, like what this means is that we're generating code at runtime for these inline caches, and this runtime code is called an IC stub. And in Firefox, this is implemented using a macro assembler, which is a lightweight kind of IR above x86, ARM, and so forth. So what this looks like in practice, like let's say we have an array. This is a typed array, so it's a uint array. And then we are iterating over this array, so from I to array.length. Now again, like array.length would normally be this really, really, really gnarly like lookup. We don't want this in practice because we loop over arrays all the time. So we want to optimize the array lookup. So in JS land, right, like we start with array.length. This has a jump instruction into the JS JIT. So the first time around, we're gonna like see that this is a typed array. The length that we're getting is a native getter. So the JIT is gonna ask like, hey, can we JIT this piece of code? It's gonna do this by running through those 32 different conditions. So it's gonna try all kinds of things. And what it's gonna find out at the end of the day that it's like, okay, well, it depends on like what the left side is of the dot and the right side of the dot. So I'm gonna walk you through what that looks like and then like what happens after the second iteration. So on the left side here, I have the first iteration, which is the callback into the JavaScript JIT. And on the second, on the right side of the screen, we have the second iteration. So like kind of the code that we generate, like what the IC stub actually looks like. So what the JIT asks on the left side is like, hey, is array an object? And if it's not, we're going to try something else. In our case, it is an object. So what we're going to do is we're going to generate an instruction called branch test object. So this is basically testing the object. And then if it's not, we're going to go to the failure case. Otherwise, we're going to unbox that particular object. The second thing we're going to do, so in the first iteration is specialize the object to something else. So is this object a typed array? And if it's not, we're going to try something else. But if it is, we can, again, optimize the thing. So on the right-hand side, because this is a typed array object, we're going to add a check, which is the branch shape pointer check, that ensures that this is actually a typed array. And finally, on the left-hand side, after we've checked that this is a typed array, we're going to read the length from the array's memory. So we're going to do the register relative read that we would do in a normal language. So what this means is that on the right-hand side, we're going to emit an instruction that just does a memory lookup. So load private in pointer is just reading direct memory. It's completely kind of a raw access. But all the stuff on the right is actually safe, right? So like we're allowed to read raw memory because branch shape pointer says this is an array. So we're allowed to read off of the array object because this is a typed array. The reason we're allowed to, again, like look at this particular, or like the reason we know that this is a typed array is because there's a separate check, the branch test object, that ensures that this is like a particular object, right? So kind of the safety of each one is implied by the previous one, and that's what allows us to read memory using raw operations. But if we look at this branch shape pointer, like what is it actually doing if we have, or if we call this function with a more general object than a typed array? So like in Firefox, if you like afterwards call foo.bar with a different bar, and this is like what happens here, is we're going to generate slightly different code. In particular, we're going to generalize this piece of code to let you work with any other kinds of object. So like what this means is we're going to change that instruction into a call VM. And we're going to basically do a more general check in this call VM that basically says like, does array.length point to typed array.prototype.length? So this is what the cache hierarchical compiler did for a while. So they were like, we generalized that previous instruction to now this new instruction that can handle not just typed arrays, but anything that could look like an array, which means that its prototype is typed array. The kind of part that they got wrong here is that this particular check does not actually imply that you're allowed to read arbitrary parts of memory. In particular, like you can create an object whose prototype is typed array, but this is not actually a typed array object, which means that now you're actually like basically allowing somebody to like read arbitrary parts of memory, and we have now a gadget that we can use and turn it into an exploitable uh, piece of code. Okay, so we need a lot of tools to get this right, and in particular, we need new tools that are not classically, or like the reason we needed new tools is because the classic ones are basically really good at verifying the engine itself, but not necessarily the code that the thing produces, right? So like we're not great at exploring the JIT code code stub that is produced by these compilers. So what Icarus does is exactly this. So like we designed a system to be able to reason not just about the JS engine, but about the code that the JS engine produces. So like if you take out the buggy typed array inline stub generator that was written in Icarus, in about 12 seconds, the buggy one, like we would flag as like, hey, this is potentially vulnerable, and here is a piece of code that you can use to actually exploit the thing. Um, what this looks like, or like kind of like how you'd write the thing to begin with, is you'd write your compiler in Icarus. So this in our DSL, you'd write your target instruction. So kind of we have our source language, which is cache AR, our target language, which is like macro assembler. You'd write that in Icarus as well, and then you'd define the semantics for macro assembler as an interpreter that Icarus can run. So this is kind of like the thing that gives the language semantics is you write an interpreter for it. And if we combine these three things in one language, we're able to effectively symbolically execute this piece of code and decide safe or unsafe after running it through the whole pipeline. Right. And like kind of the way to like think of like, okay, like what is the thing that we're verifying? But your JIT security contracts end up being like, what is our compiler doing? And then I have my interpreter, which says like, hey, this load instructor is an unsafe instruction. And I want to have basically an assertion here that says that this is actually a read that is in bounds. And what makes this hard again is we're not looking at a single program, we're looking at many spaces of programs. So we're looking at program generators themselves. And the other thing that I think is worth pointing out that it's not just like a compiler proof. We're thinking about a JIT, so there's like runtime conditions we need to take into account, and in particular, there's conditions and invariants that we have at runtime that imply the safety of the code that we generate at runtime again, right? So it's not just like, is my compiler producing the correct code? It's actually like, what are the conditions in my compiler at right now for the code that I'm generating right now? And like we need to take those safety conditions within the compiler and thread those through for the generated code. And kind of like what we're doing here is taking all those bits, shoving them through what we're calling symbolic meta execution, because if you were to just do symbolic execution off the shelf, that would totally not work. And I'll give you kind of like an intuition for slightly like where things would get stuck. Um, in particular, kind of the way to look at like what Icarus is doing, we've taken the JIT, we've lifted it to this DSL, and at runtime, we're emitting instructions, right? So we're generating code at runtime. So our symbolic compiler is producing symbolic generated code, and we have an interpreter over the symbolic instructions because we need to actually have some semantics for like what is the generated code actually doing. So this is where we have our little interpreter. But like we would really get stuck here, right? So like we're talking about an interpreter that's symbolically executing a symbolic number of instructions, and all those instructions are themselves symbolic. The way we solve this is by effectively JIT compiling the interpreter itself. So like instead of having the general loop that we kind of like would for any instruction that is like 32 nested cases down, we would specialize the interpreter for the thing that we're compiling. So we're compiling this particular generator. We can actually say like you will never emit an add instruction when you do a property lookup. So we shouldn't be exploring that particular path. So like the only thing that we need to do is to kind of statically analyze what your generator looks like, and then you can specialize the interpreter based on just instructions that it would ever possibly generate. So there is certainly like here, the optimization does depend on us getting this static analysis right, but it's a really lightweight static analysis, and it's really simple to ensure that like you're not considering instructions that don't actually matter. You can be pretty conservative in your analysis. Okay, so again, like running the buggy thing in 12 seconds, we're able to say this is unsafe, and what we would get is an output that says like, hey, this line of code, where we have an assertion that says the slot that we're accessing or the memory that we're accessing is within bounds, is not actually satisfied. So this assertion actually fails. So we shouldn't be performing the unsafe thing, which is the actual get fixed slot instruction, which is the implementation of the raw read that I saw earlier. Right. In particular, it's going to tell you that like, hey, I can't prove that this always holds, and then you need to fix it. And like when we fix that particular IC generator implementation, after 7 seconds, we're able to prove that this thing is safe. Now, what did we actually verify using this DSL? Um, well, because of this is roughly like just a one effectively one grad student porting this thing, we are only able to port like a fraction of Firefox, but it's still, I would say, like a pretty meaningful fraction. So it's like roughly like 20% of like the different parts of the cache AR bits. So we ported 21 out of the 270 generators. So this is the code that's generating all the macro assembler code. And we ported 81 cache AR instructions and 131 macro assembler instructions. So we kind of have like baseline definitions for these different IRs, and then 21 implementations of these effectively like compilers. The way is one way to look at it. And kind of the security properties that we ended up encoding are things like memory access, bound safety, like ensuring type safety when you're compiling, and ensuring that your register allocator is correct, and ensuring that when you're calling into the JS runtime, that interface and that call is actually safe. So we're able to like encode a bunch of these security properties as assertions and assumptions, kind of like in the classical style, and prove those things statically. Okay, so with that, I'm gonna leave you here with just kind of like maybe a sample of like uh where I think we want to go. So the question is like, okay, we've ported a fraction of the inline cache bits of Firefox. The question is like, okay, should we port the rest? I think that's what we're exploring now, is we're going to try to actually use LLMs like our Startle to see like, can we actually port the rest of cache AR and the rest of these generators to Icarus with the assistance of LLMs, because like doing it manually is way too expensive, and there's no way that we can get all the Firefox folks to jump on board until we actually ported more of this, because it's just like way too much of a lift to say, please use our DSL to implement now this part of Firefox. And once we do that, I think, or like even if we don't do it, I think the question is then like, okay, like what should we be thinking about? What are the bits that we should rewrite? What are the bits where current tools aren't finding bugs in effective ways? And where does verification actually make sense, given that, well, like kind of the landscape seems to be changing at least a little bit, and that these tools can both be more usable with some automation, and that folks are finding bugs and eliminating bugs using other techniques. But I'm already over time. Sorry for going a bit over, and I'll stop here.
All right. Thank you for a super interesting talk. If people have questions, please add them to the comment sequence. We have time for a couple of follow-ups. While we're seeing if there are some audience questions, let me start with a couple of these here that I had. One interesting technical question I had is in the first part of your talk on sandboxing, you were able to remove context switching code, and that actually surprised me. It's clearly a big performance win. But is this tied to your decision to use WASM-C? Because it was hard for me to imagine that if you're doing that with a WASM virtual machine, maybe especially one that might use JIT compilation or something, that might be quite difficult to do.
Great. Yeah, that's a really good question. So okay, we should be able to do it for any WASM compiler. So I would say like, even if you so like, in fact, we did this for CraneLift before we actually went back to WASM to C.
Oh.
So in the original CraneLift implementation, we actually got rid of the trampolines that were doing the register saving, restoring, and clearing. So you can actually do it. I think for a JIT, it should be doable as well. So like if you actually look at the implementation of these WASM bits in Firefox, they're already kind of doing stuff like this when JS calls into WASM and back. So they've I guess like had maybe the observation before we did that this is totally cool to do. I guess we just have formal proofs that it's okay to do. WASM to C does make certain things better though. So in particular, um, and this is actually still a thing that I'm currently looking at to trying to like have a formal proof for, or and I'm kind of scared a little bit of like what that might look like. But because we're compiling to C, um, so we're taking C, compiling it to WebAssembly and back to C, and then we're linking that against Firefox. So it's just functions across the boundary, basically. One of the things that we're able to do here is now let the optimizer rip. In particular, like we can have LTO and performance guided optimizations that are going across the boundary, right? So like previously, like if you're saying like,
Okay.
here's
Yeah.
dynamic library, it's in a sandbox, don't look inside. So then we have a nice condition and we could say like, okay, like you're allowed to jump back and forth. One of the things that we're able to do now is actually optimize across the boundary. Um, I
Yeah.
think
Okay.
it's
That's
safe,
nice.
but under
So,
certain
so,
conditions.
so in the JIT setting, I guess you're relying on the fact that even though this thing is opaque, it's probably just using standard x86 or whatever your platform is, calling conventions and so on. So
Exactly,
they could in
exactly,
principle choose something different, but they don't.
exactly.
Yeah. Yeah. Okay. Excellent. So you mentioned deployment in Firefox. I wonder if you could say a little bit more about kind of your experience of the Firefox team using RLBox and yeah, how that went.
I guess we've been working very closely with the Firefox teams for now, I guess maybe over a decade. And I recommend everyone honestly work with the Firefox team. They're awesome. And particularly they really care about actually taking kind of research ideas that are practical and shipping them into browser and really trying to address the like we care about our users problem and we care about the security of those folks. So we worked very closely with them on kind of getting the first version with Greenlift. So this is working both with the security team and Bobby, who's now the CTO, on hey, like we want to experiment with this thing. We're getting security wins out of here, and then we worked with I forget. I think it was Paul Adenaught on the like actually integrating this thing for rendering glyphs. Um, and helping us basically measure the things. Like one of the hard bits is figuring out like uh what is a meaningful performance metric. So like you can render a page and see like, okay, it doesn't actually impact the thing. They have a bunch of benchmarks that they internally run, but at the end of the day, it's like there's an expert who knows whether or not this thing is shippable because they have some other internal benchmarks and some intuition for like why a thing um performs well enough or not. So like kind of at every point we ported libraries, we worked with different teams to like make sure that okay, the thing we ported is fast enough. And a bunch of cases, like it was not. So for like a bunch of libraries, like libsuntouch, which speeds up and slows down kind of voice or like audio. Like our initial version was like definitely not fast enough because like we were only able to compile the C library that didn't use SIMD. So like everything was slower now if it was sandboxed. So that one we ported to RLBox, so we kept around the types that say like, hey, we can use a sandbox once we have a good sandbox. But it took like another year for us to get SIMD into WASM2C. And then we're like, okay, the performance is finally reasonable enough. It's on the order of like, I don't know, 15% or something where this is okay to ship. Like the voice is not weird if you're dilating it or speeding it up.
Right. Yeah. Nice. Okay. We have another question. Congratulations on not saying LLM is the answer. What languages would you recommend an undergrad CS student interested in browsers and isolation learn first and later? We should probably make this the last question because we need to give people a little break before the next session.
Um, it's a weird take, but I think Rust. I think right like the learning curve is a little steep, but it's not that bad. I think just like with anything else, start building a thing and then like just you'll pick it up. It's not like I find it like I hack on browsers every so often, and like I used to like commit part to parts of Firefox, and then I would stop because I have to do the faculty thing and not commit again, and then I would just like get this anxiety of like, what does the equal sign mean for like the C++ dialect within Firefox? And I'm like, I go back to Rust in similar ways nowadays. I'm like, this is less weird. Equals is pretty well defined here. So
Yeah,
I think it's a great language. It gets you into guts, and now more parts of the browser are in Rust. So like that'd be what I do.
great. Yeah, I endorse that answer as I'm teaching a systems programming in Rust class this fall. So
Nice.
wonderful language. Okay, well, thank you so much for your presentation. It was super interesting and right on target for science of security. Let's give people 4 minutes of a break before the next session. And yeah, thanks again.
Thank you all.